But just to set the scene, let me start by saying that I'm a condensed matter physicist, and the governing slogan of condensed matter physics is the idea that more is different, which is to say, if you have many degrees of freedom all interacting together, you can get qualitatively new phenomena, which now don't arise in few body systems. So a classic example of this would be superconductivity. You can take the one electron Schrodinger equation and work at it until you're blue in the face, and you'll never find superconductivity. It's just not there. But take many electrons all interacting together, cool down to low temperature, and you go into a new sort of phase of matter, a superconductor, which supports dissipationless current, has Meissner effect, and what have you. And a key part of condensed matter theory is really the search for these sorts of new emergent phenomena. And historically, condensed matter theory has focused mostly on systems in thermal equilibrium, where the possibilities are comparatively well understood, by which I'm not saying that everything is known, but certainly we have a large toolbox of standard techniques, essentially based on ideas of thermodynamics and statistical physics, with which we can go about finding the answers. Now, in contrast, non-equilibrium systems are terra incognita, and they can support qualitatively new phases of matter with no equilibrium analog. So something we pointed out a decade ago is that, in the non-equilibrium setting, you can have new possibilities like spontaneous symmetry breaking at non-zero energy density in one dimension, or topological order without an energy gap, which don't make any sense in thermal equilibrium, cannot occur in thermal equilibrium. Yeah? And since then, the exploration of non-equilibrium phases of matter has become a big field in its own right. Now, probably time crystals are the most famous example thereof, and at Stanford, I imagine, you know all about those. But at the broadest level, I would say that, look, understanding non-equilibrium phases and the sorts of phases that can arise in the non-equilibrium setting, this is one of the great challenges, maybe the great challenge for condensed matter theory in the 21st century. And it's been like one of the main things I've been working on for the past decade. Now, the way I'll set up the talk is as follows. So the talk ultimately is going to be about non-equilibrium physics, but I'll start off by explaining equilibration. I'll introduce the notions of quantum thermalization and ergodicity, which will provide a counterpoint to the non-equilibrium physics, which I will subsequently discuss. Now, the key non-equilibrium physics is going to draw on insights drawn from the study of a new sort of quantum phase of matter, the fracton phase. So then I'll give you a quick introduction to fractons. I will then explain how we can take principles derived from the study of fractons and use them to robustly break ergodicity and sustain new sorts of non-equilibrium phenomena. I'll then introduce you to a topic I refer to as fracton hydrodynamics, before finally concluding and giving you some outlook. So, without further ado, let's start by discussing equilibration. Now, traditionally, when we study stat-mech, we consider a system which is connected to some kind of reservoir. So maybe one thing to check. People that are in the live audience, you can just ask questions right away. People that are in the Zoom audience, if you have questions, maybe you could just unmute yourself and ask, because it's hard for me to sort of track questions in the chat at the same time. Or maybe if somebody's in person and is also on Zoom, you could sort of monitor the questions in chat, and if there's questions, just call them out. Okay, so traditionally, when we do a stat-mech, we have a system that's connected to a reservoir. So the question I'm asking today is slightly different. I have a collection of quantum degrees of freedom, and these could be cold atoms in an optical lattice. They could be trapped ions. They could be NV centers in diamond. They could be cold circuits. They could be whatever your favorite sort of quantum information processing architecture is. But it's some collection of quantum degrees of freedom, or qubits, that are well isolated from the environment, but are all interacting with each other. Yeah? And as an isolated quantum system, their state is described by a wave function. That wave function is psi. Its squared gives the probability density. And this wave function evolves in time according to the Schrodinger equation written here, with the time dynamics being generated by a Hamiltonian. And the question that we'd like to ask and understand the answer to is whether the Schrodinger time dynamics of the system brings it to thermal equilibrium in the long time limit or not. Yeah? Well isolated but many particle quantum system, does it go to thermal equilibrium? Now, there's a high-level objection you could raise, which is the following. The process of equilibration is associated with a loss of memory of the initial conditions. So I have a cup of coffee, I pour milk in, I wait a while, after it's equilibrated, it's gone to a uniform light brown color, it doesn't know about the initial condition. Yeah? Or another way to put it is that systems in thermal equilibrium are fully characterized by temperature, pressure, and a handful of other variables, and they don't remember their initial condition, which you might think is a problem because a quantum mechanical time evolution is unitary, which means it preserves all information about its initial condition for all times. So how do we reconcile the unitarity of quantum time evolution with the apparent loss of memory of the initial conditions needed for equilibration? And the resolution is that, look, now we don't have access to all of the information contained in the quantum wave function. The only measurements we can make are few body measurements made locally in real space. And so the meaningful question is, do accessible measurements, few body measurements local in real space, do those appear to see thermal equilibrium or not? Yeah? Because if the only way to extract information about the initial condition is to fully reconstruct the wave function, well, that's not possible, even in principle, really. And this leads us to the notion of quantum thermalization, which is all about subsystems. So I take my many particle quantum system and I carve it up into a subregion A and everything else B. And A is the subregion that I'm measuring. And now I can ask, can B serve as a reservoir for A? And if B can serve as a reservoir for A, then I'm effectively solving a system coupled to a reservoir problem, where now my system is A and my reservoir is B. And now I might expect standard statistical mechanics to apply. And there's strong numerical evidence that many isolated quantum systems do thermalize in this way. And if quantum thermalization occurs, then the usual sort of law of thermodynamics and statistical physics applies. And this brings us to a very important concept in statistical physics, which underpins our understanding of thermalization, which is known as ergodicity. So states of a system, you can talk about macrostates. So the macrostates are characterized by the measurable properties of the system, such as temperature and pressure and what have you. Whereas the microstates contain detailed information about every particle. And there's gazillions of microstates for every macrostate. Now, there's many ways to arrange the particles while having the same temperature, pressure, and so forth. And there's a foundational idea which dates all the way back to Boltzmann, and this is the idea of ergodicity, which says essentially that the system explores all of the microstates consistent with the macrostate it's in. Or maybe a more precise way to say it is, maybe the system has some conserved charges, charge, energy, and it explores all of the microstates that are consistent with those conservation laws. So all of the microstates that have the right charge, right energy, and so forth. And if this ergodic hypothesis is obeyed, then we can apply usually standard statistical physics. Whereas if the ergodic hypothesis is violated, so if ergodicity is broken, then this is, here there be dragons territory. So at the end of the day, we want to get to non-equilibrium physics, so I'd really like to find a way to break ergodicity. How can we go about breaking ergodicity? There's a few ways that we know of for how to do it. The first and oldest and best explored is integrability. So integrable systems, and I'm talking specifically about integrable quantum systems here, they have an infinite number, an extensive number of conservation laws, and this allows them to evade ergodicity. But with integrability in the quantum setting, it's not known how robust this is. So it could be that the moment I perturb the system with arbitrarily weak perturbations, the integrable structure could go away, ergodicity could get restored. There's another way to do it, which is the phenomenon of many-body localization, which has had a great deal of interest and a great deal of work on it in the 21st century. So what happens with many-body localization is, again, you get an infinite or extensive number of conservation laws, but this time, instead of being put in by hand in the Hamiltonian, Instead, they emerge naturally from the dynamics of the system. And this allows the system to break ergodicity. And moreover, this ergodicity breaking is provably robust to arbitrary short-range perturbations. Yeah? However, the phase is only proven to exist in one-dimensional spin chains with strong disorder and short-range interaction. So that's a fairly restrictive setting in which the phenomenon is known to exist. Yeah? But within this restrictive setting, it's great, provably robust ergodicity breaking. And if you had asked me 5 years ago, I would have said this is it. These are the only two ways that I know of in which you can break ergodicity. However, in the past couple of years, we've discovered that it's possible to actually break ergodicity with only finitely many conservation laws, and in fact, just 2 conservation laws will suffice. And the key insights for how to do this comes from the study of a new area of physics, fractons. So
what about spin glasses?
What about spin glasses? Okay. Well, for spin glasses, as best as I understand, the jury is still out whether if you wait to infinite times, the problem thermalizes or not, right? So there's the world of glasses in general, there's this long-standing debate. So what exactly, I mean, are we talking classical spin glasses? Are we talking quantum spin glasses?
Classical.
Yeah, okay. So, I mean, I have nothing to say. Yeah. Right. So, no. So for the moment, I'm only talking about quantum systems. Yeah. So for classical systems, there are ways to break ergodicity. So there's spin glasses. There's also the integrability. So in classical systems, I guess there's a CAM theorem. So even integrability can be robust to perturbations, right? But for quantum systems, we don't have an analog of the CAM theorem. Yeah? So today's talk is specifically about ergodicity breaking in quantum systems. Yeah? And kind of as of 5 years ago, I would have said the only ways I know of to do it are either integrability or many-body localization, and they both have infinitely many conservation laws. Whereas in the past couple of years, we've discovered a new way to do it, which instead of infinitely many conservation laws, only relies on 2 conservation laws. You have to pick the right 2. Okay, so now, what are fractons? This is what's going to teach us how to break ergodicity. Well, fractons are a new kind of quantum phase of matter. They were originally discovered in 3 space dimensions, although by now we know how to get fracton-type phases in lower dimensions as well. And their defining feature is that the excitations exhibit fractionalized mobility, meaning the elementary excitations are either totally immobile or they're able to move only in certain directions. And this provides a new way to robustly evade equilibration, as I will show. And once we understand how to do this with fractons, in fact, we'll be able to abstract away and get the necessary physics without fractons, but we discover it in the context of fractons first, so that's how I'll present it. It's always nice to illustrate things by example, and the cleanest example I know of a fracton phase is the model that's known as X cubed. So this is an exactly solvable model. It has an extremely Baroque Hamiltonian, which would never be realized in any system, but this Hamiltonian is not written down for realism, it's written down for sort of analytical tractability and exact solvability. Yeah? But it describes a phase, and this phase could arise even with a Hamiltonian that's more simple and not this crazy Baroque. So what is the X cubed Hamiltonian? Well, this is a model that's defined in a cubic lattice. So you have a cubic lattice, and on every link of the cubic lattice, you place a single spin half variable, so a single qubit. And remember, the wave function is the state of all of these spins, which live on the links of the cubic lattice. And the time dynamics is generated by a Hamiltonian, and the Hamiltonian consists of 2 sorts of terms, A's and B's. The A is a product of Pauli X operators on the 12 links that frame an elementary cube, and the B's are products of Pauli Z operators on the 4 links that connect to a vertex and lie in a particular lattice plane, either the XY or XZ or YZ lattice planes. Yeah? And we want to talk about the properties of this Hamiltonian, and specifically the dynamics which is generated by this Hamiltonian, possibly plus small perturbations, arbitrary small perturbations about this Hamiltonian. Now, one thing I should say is that these A and B operators They all commute with one another, which means they can be simultaneously diagonalized. And the ground state, the lowest energy state of the system, has eigenvalue +1 under every A and every B operator. Yeah? So let's consider a system that's prepared in the ground state, so it has eigenvalue +1 under every A and B operator. And now let's imagine acting with a single Pauli Z operator on a single link. Now, this commutes with all the B operators because they're made of Z's. Yeah? However, it anti-commutes with every A operator that contains this link. So it leaves us in a state that has eigenvalue -1 under the 4 cube operators that contain this link. And so we're left with 4 excited cubes. Now let's act with another Z. Now I have 2 anti-commutations in here, so those have eigenvalue +1 again. And I have eigenvalue -1 on these 2 cubes and on these 2 cubes. And now more generally, let me imagine acting with a membrane of Pauli Z operators. So everywhere far away from this membrane, I've done nothing to the state. In the interior of the membrane, I've had 4 anti-commutations, but -1 to the 4 is 1, so that's still satisfies, still has eigenvalue 1. Everywhere along the edge, I've had 2 anti-commutations, but on the corners, I've had a single anti-commutation. So what acting with this membrane of Z operators does is it leaves us with a single excited cube at each corner of the membrane. And now you should be able to convince yourself that there's no local perturbation which allows you to move these corner excitations around without creating additional excitations. Yeah? You can move them by creating additional excitations, but the only way to move them without creating additional excitations is to expand, contract, or otherwise deform this entire membrane, and that is a highly non-local operation. So these guys are immobile under local Hamiltonian dynamics. Okay. So no, they have this restricted mobility, these elementary excitations which are made at the corners, they're given their own name, they're called fractons. Moving fractons costs energy, and what this means is that at 0 temperature, in fact, they're perfectly immobile, and you plop down some set of fractons and they cannot move because there's nowhere to get the energy from. Moving them costs energy, and there's no source of energy in the problem if we're at 0 temperature. But more generally, for quantum dynamics, we're interested in problems at non-zero energy density. So what happens at non-zero energy density? So we explored this in this paper here. What we said is we essentially took the exactly solvable lattice models, like the X-cube model or the Haas code model, and we treated the dynamics using methods drawn from localization and the study of stabilizer codes. And we concluded that in fact the system does equilibrate at any non-zero temperature in a finite time. It's just that time scale is long. Yeah? So for the most iconic of the solvable lattice models, the Haas code model, the equilibration time scale is finite at any non-zero temperature, but it diverges as temperature goes to 0, and it diverges faster than exponentially. It diverges as x1 over temperature squared. Yeah? So it's a very rapid divergence, faster than Arrhenius. There's a very long time scale that it takes for the system to equilibrate, but at the end of the day, all we're doing is we're losing more slowly. Yeah? We're still going to equilibrium, it's just taking a long time to do so. Can we find a way to actually win and to never go to equilibrium at all, even at infinite times? So the answer turns out to be yes, but to understand how to do this, we're going to need a complementary way to think about fractrons. And this is a way that was sort of come up with by Michael Petko, my genius former postdoc. And what Michael said essentially is that, look, you can think of these constraints on fracton mobility as arising in a very natural way from some generalized gauge theories. And his logic was essentially the following. So if we were doing familiar gauge theory, like Maxwell electromagnetism, then we would have a Gauss law constraint, like divergence of E is electric charge. And this Gauss law constraint, it implies a conservation law for charge, because if you want to calculate the charge in a unit volume, you can use Gauss's law to rewrite this as a volume integral of div E, and now you can use divergence integral to rewrite this as a surface integral, and if the electric field is fixed on the boundary, then the charge enclosed by that boundary must be conserved. Now, traditional gauge theories are written in terms of vector gauge fields. And the key question that Michael asked is, what if instead we wrote down a gauge theory in terms of higher rank tensor gauge fields? Yeah? So now we want to write down a gauge theory that involves symmetric tensors. Yeah? Rank 2 is sufficient. So now the Gauss law will look something different. So it might look something like di, dj, eij of rho. And this kind of generalized Gauss law encodes additional constraints in addition to charge conservation. So for instance, if you consider this integral, which gives you the dipole moment, yeah, you can use the generalized Gauss law to rewrite it in terms of the electric field. And then you do an integration by parts and use the divergence theorem, and you conclude that if the electric field is fixed on the boundary, or if there isn't a boundary, then the dipole moment in the system must be conserved. Yeah? So if you write down a gauge theory with symmetric tensors, then you can naturally get something that looks like conservation of dipole moment. And conservation of dipole moment has a consequence that looks very fractonic. So if you have a single charge, yeah, a single charge cannot move, because if a single charge moves, then it changes the dipole moment. Whereas if you have two charges together, they can exhibit correlated motion in a way that keeps the dipole moment constant. Yeah? So this encodes something that's a lot like the Fracton constraint, where single excitations cannot move, but multiplets of excitations can move in some correlated fashion. Yeah? And since then, there's been a lot of work in how you can actually get the exactly solvable, or how you can get the Fracton phases in terms of symmetric tensor gauge theories. But that's not the story that I want to tell you about today. What I want to tell you about today sort of starts with this observation that you can think of the Fracton constraint as coming from the existence of conservation laws on multiple moments of charge. So dipole moment conservation being the simplest example. And the exactly solvable models like the X cube or the Haas code, which I told you about, those have discrete Z2 type conservation laws on multiple moments of charge. And the real payoff for evading equilibration comes about when we promote from Z2 type conservation laws to U1 type conservation laws. Yeah. So for the rest of the talk, we really want to consider problems which conserve charge and conserve dipole moment or additional multiple moments. But the charge and the dipole moment or the other multiple moments are now defined as U1 quantities. Yeah, so they can be integers, they're not discrete. I mean, they're not Z2, they're U1. And this might seem extremely baroque, but as we'll see later on in this talk, actually, there's various natural experimental realizations for these sorts of U1 charge and dipole type conservation laws. But for now, let's just assume we have these conservation laws and run with it. So what does this do? Well, now everything should be made as simple as possible. And the simplest setting in which we can realize, yes, Sri.
You just described pure gauge theory. How do you couple the matter?
Yeah.
That's
right. So, I mean, yes. So there's a large body of work on how you get the Fracton models from considering some symmetric tensor gauge theory coupled to matter. That's not a story that I'm really going to be telling you about today. So all I want you to take away from my discussion of gauge theories is that you can think of the essential Fracton phenomenology as arising from the existence of conservation laws on multiple moments of charge. Yeah? Now, in the context of the Fracton phases, you can think, now you have some generalized spin liquid, it has an effective low energy gauge theory description in terms of symmetric tensor gauge fields, they have some generalized Gauss law, which then gives rise to this multiple moment conservation. But I don't actually need all of that structure. Yeah? What I'm going to do from now on is just say, I will assume that I have dipole moment conservation coming about for whatever reason. Now, it could be coming about from some effective symmetric tensor gauge theory, or it could have a much more mundane origin. And I'll give some examples of like more mundane origins later on in my talk. Yeah? And now I just want to explore the consequences of this additional conservation law. Yeah? And that's what the rest of the talk will be about. Okay, so everything should be made as simple as possible. We want to consider quantum dynamics, which conserves charge, conserves dipole, and is generated locally in real space. Yeah? And the simplest setting I know of for doing that is a one-dimensional spin chain, and spin one chain is convenient. So we consider an array of degrees of freedom in one dimension. And on every site, I have a single spin 1 object. So that's a 3-state system. It can be +1, 0, or -1. And I'm considering a quantum dynamics which conserves the z component of the spin. So the charge is just given by the z component of these spins. And the dipole moment is defined in the obvious way as the position-weighted charge. And we can assume I'm working with open boundary conditions. So now, if I conserve dipole moment, then a single charge cannot hop about, because if a single charge hops, that changes the dipole moment of the state, and that's not allowed. Dipole moment is a conserved quantity by postulate. But if I have a plus charge and a minus charge close together, that can move freely. Yeah, that doesn't change the charge or the dipole moment of the theory. So this is a mobile object. And I can also have the following kind of process, which you could interpret either as charge hops right and emits a plus-minus dipole to the left, or as charge hops left and emits a minus-plus dipole to the right. Yeah, this sort of process, for instance, is also allowed. It conserves charge and dipole moment. Yeah? And there's also sort of more longer range allowed processes, which give sort of correlated motion of charges and dipoles. So we want to study quantum dynamics, which conserves charge, conserves dipole, and has spatial locality. And we don't want to put any other constraints on the problem. Yeah? So the minimally structured realization of this idea is in the context of a quantum circuit model. So what's the idea behind a quantum circuit model? Well, quantum mechanical time evolution is always generated by a unitary matrix. So you have a wave function and you act on the wave function with a unitary matrix, and that gives you the time evolution. Yeah? But if you're considering dynamics that's locally generated in real space, then you want that big unitary matrix to be made up of a bunch of little unitary matrices which act on contiguous regions in real space. Yeah? And the idea behind the quantum circuit model is that you generate the dynamics by taking a bunch of little unitaries which act on local regions in real space, and then you concatenate them to make a big unitary which generates the time evolution. Yeah? And if you're doing circuit dynamics, then you call these little unitaries gates. But no, more generally, if you're not used to thinking of circuit evolution, if you're more used to thinking of Hamiltonian evolution, you can think of the Suzuki-Trotter decomposition of the unitary, where you take the unitary time evolution matrix, you carve it up into little time slices, like the way when you're setting up path integrals, and each of those time slices gives you a bunch of little unitaries acting on sort of spatially contiguous regions, and you can think of these as little unitaries in your Suzuki-Trotter decomposition, if you prefer. But the point is, we want to consider quantum dynamics, which is generated by a bunch of little gates or little unitaries acting locally in real space. And we want these gates to preserve charge and dipole moment, which means we want them to be block diagonal by charge and dipole symmetry sector. But other than that, we place no constraints on the problem. So within each charge and dipole symmetry sector, these gates could just be a random matrix. Okay? And now we concatenate them, build up the unitary, and see what it gives us. So what should we expect to get? Well, so one thing I should say is that these unitaries, they can be chosen to be uniform in space or random in space. The answers don't change. And they can be chosen to be uniform in time or random in time, and the answers don't change. Yeah? And sort of the results are maximally dramatic if you choose them to be uniform in space and random in time. But it doesn't really matter for the purposes of what I'm going to say. Now, what should we expect? Well, quantum dynamics is restricted to a symmetry sector. So you start with a particular charge and dipole moment, and you remain with that charge and dipole moment forever. But if you have ergodicity, then you would expect that at long times, you cycle through all of the states that have a given charge and dipole moment. So what's shown on the left is what the sort of long time average, or what the charge density distribution would be for an equal weight superposition over all configurations, all microstates in a given charge and dipole sector. And what you can see is it looks basically flat. So if you have ergodicity, then charge ends up spread uniformly over the whole system in the long time steady state. What's shown on the right is you start off with charge sitting in a particular site, here number 4, And then you generate the time dynamics by acting with this bunch of gates, and you look at the charge at late times. And it looks very different. Yeah, the right side does not look like the left side. When you do the actual time dynamics, the charge stays close to where it started off. It looks localized. It does not look ergodic. So the actual time dynamics appears to break ergodicity. And this is weird, weird for various reasons. This looks like localization, but it cannot be conventional localization. So one way to see this is that this doesn't rely on having spatial disorder, and conventional localization does. Another way to see this is that conventional localization relies on energy conservation. And you can get this even if you choose the gates to be random in time. And remember, energy conservation by Noether's theorem is tied to time translation invariance. So if you don't have time translation invariance, there's no energy conservation. Yeah? You're looking at stochastic, noisy time evolution. And conventional localization definitely doesn't work with stochastic time evolution. And it also can't be integrability, or you wouldn't expect it to be integrability, because integrability usually relies on very fine-tuned Hamiltonians, whereas here, the relevant Hamiltonian needs symmetry sector is just made up of a bunch of random matrices. Okay? So now this looks like localization, it looks like it's breaking ergodicity, but it doesn't seem like it should be either integrability or conventional localization. For the minimal model I gave you for three-side gates, almost any initial condition breaks ergodicity. For longer range gates, typical initial conditions actually thermalize, but there's still a vast number of initial conditions which do break ergodicity, and it cannot be conventional localization. So originally we just we observed this numerically. The explanation for what was going on sort of emerged in these other papers, and now I'll share it with you. So let's consider a state of the following. So we're considering quantum dynamics that conserves charge, conserves dipole, and is locally generated in real space. And let's say we have a state which is of the following form. It's all plus, then all minus, then all plus, then all minus. So here plus is the state of locally maximal positive charge, and minus is the configuration with locally maximal negative charge. Yeah. So this state has a bunch of domain walls in it, where the pattern changes from all up to all down. And those domain walls are at least as far apart as the biggest gate that's generating my dynamics. Yeah. They're at least as far apart as the biggest unitary that generates time dynamics. Now let's consider the dynamics of this state. So I come in and I act with a bunch of unitaries, and each of those unitaries acts across either 0 or 1 domain walls by construction. It can never act across 2 domain walls because the domain walls are further apart than the biggest unitary I have to act with. If it acts across 0 domain walls, it acts in a state that's locally extremal charge, and there's nothing you can do to that consistent with charge conservation. If it acts across 1 domain wall, it acts across a state that's locally extremal dipole, given its charge, and there's nothing you can do to that consistent with charge and dipole conservation. So if you try and shuffle the plus and minus charges around in here, you'll necessarily change the dipole moment, and that's not allowed. So any state of this sort must be an exact eigenstate of any dynamics that conserves charge, conserves dipole, and is locally generated in real space on the scale m. Now, how many states like this are there? It's easy to place a lower bound. You can take your system, you can carve it up into blocks of size m, and each such block you can allow to be either all plus or all minus, and this gives you at least 2 to the L over m states, which are product states from the charge basis, and are exact eigenstates of any dynamics that conserves charge, dipole, and space, and is locally generated in real space. Yeah? And if you pick any initial condition that's in the part of Hilbert space spanned by these special states, essentially you'll have no dynamics of charge. Yeah? So this is a localized subspace of size exponential in system size. And I should say that this count is not tight. Yeah? This is just a lower bound. You can get a tight counting by doing transfer matrix, but it's more involved, and it just changes coefficients in the exponent, and this simple argument is sufficient for establishing the existence of a large subspace. Yeah.
Did you say what capital L is in this formula?
So capital L is system size, and little m is the size of the biggest gates I have.
Thank you.
Okay, so this gives this this large localized subspace. We can also look more generally. So time evolution is always generated by a unitary matrix. The unitary matrix is always block diagonal by symmetry sector. Yeah, so different symmetry sectors don't talk to each other. You start off in one symmetry sector, you don't end up in a different one. But in ergodic systems, that's it. Yeah? Each symmetry sector is a random matrix. Here, we get something that looks very different. What we find is that within each symmetry sector, the problem further block diagonalizes. And all of these exact eigenstates, they're 1 by 1 subblocks. They don't mix with anything else. Then you also have 2 by 2 subblocks, two states which mix with each other and not with anything else. 3 by 3, 4 by 4, very broad distribution of subblock sizes, including some with size that diverges in the thermodynamic limit. But importantly, the fact that you have this massive block diagonalization within each symmetry sector means you don't end up exploring the entire Hilbert space within the symmetry sector. Yeah, so you have manifestly broken ergodicity. This generalizes straightforwardly to higher dimensions. So suppose you were in 2D and you conserve charge and dipole in both x and y. Yeah. So the simplest thing you could do is you could just take the states I just talked about and extend them in translation invariant fashion. And that will give you a number of eigenstates in a localized subspace that's exponential in linear system size. But you can do better than that because you can actually allow these stripes to roughen a little bit while remaining localized. And this gives you a number of states that's a localized subspace that's actually exponential in system area. And the construction generalizes to arbitrary dimensions. So if you're in d dimensions and you conserve charge and all components of dipole moment, then you have a localized subspace which is exponential in system volume. And it's this sort of very simple, sort of two-line proof. And there's nothing to argue about. It's just manifestly localized in this subspace that's exponential in system volume. And you can also get this sort of physics with higher multiple moment conservation, where even more exotic possibilities arise. Now, can we realize any of this in some reasonable physical setting? Yeah, in the back.
Systems,
yeah.
The case of the entire Hilbert space is localized, as opposed to just an exponentially large subspace?
Well, I mean, integrable systems have an extensive number of conservation laws. Yeah. So the unitary matrix massively block diagonalizes by each symmetry sector, right? So and you have this vast number of symmetry sectors. But within each symmetry sector, you would still expect ergodicity. And that's the idea of the generalized Gibbs ensemble. Yeah? What we have here is different. We don't have that many symmetry sectors. Yeah? We definitely don't have extensively many conservation laws. But within each symmetry sector, we don't have ergodicity anymore. So, physical realizations. Yes, there are physical realizations. One nice realization is just ultra-cold atoms in an optical lattice where you put the whole system in a tilted potential. Yeah? So the center of mass of the system couples to potential tilt. The center of mass can't easily move up or down because that would change the energy, and we're considering isolated quantum system with conserved energy. So you get center of mass conservation. And center of mass here is analogous to dipole. Now, strictly, it's center of mass conservation only up to some pre-thermal timescale, which is exponential in the tilt, but that timescale can easily be bigger than experimental timescales. And this phenomenon, I mean, what you would expect is if you had cold atoms in a tilted lattice, then you would expect exquisite sensitivity to initial conditions. So you pick an initial condition, which is one of these 1 by 1 subblocks, one of this localized space, and you have no dynamics. You pick an initial condition, which is in one of the large subblocks, and you get very rich dynamics. And this physics has essentially been seen by 2 different experimental groups. There's also additional proposed realizations. And there's other realizations as well, which I'm going to skip talking about for time, but this is one very concrete realization, which has already been observed in the laboratory. And note, there's no fractons in here. Yeah, we sort of figured out a way to do this by studying fractons, but the key phenomena, it turns out, you can actually realize without fractons in the picture at all. So to summarize the first part of my talk, if you have fractron models with discrete conservation laws, you get glassy dynamics. But if you promote to U1 type conservation laws, then you get what looks like true localization in a subspace that's exponential in system volume in any dimension. And this can be rigorously proven, doesn't require disorder, and it's robust to temporal noise. It does require strict locality, and it requires sort of strict conservation of charge and dipole, and it can be realized in the pre-thermal sense in various experimental platforms. Yeah.
Do we know that since we have many smaller blocks,
Yeah.
do we know that there's no local conservation laws corresponding to those blocks? No other local.
I mean, besides which block you're in.
Yes, there's
Right.
big blocks, and then you break ergodicity.
Yeah, very good. So that brings me to my next slide. So far we were talking about these exact eigenstates, this localized subspace. Steve.
So presumably, if you have interactions even if fell exponentially, you wouldn't get localization. Just get very slow dynamics.
Right. So
Do
if
you have any idea of how slow those are?
yes. So Steve asks, what if you didn't have strictly compact sort of terms in your Hamiltonian, if you had some exponential tails, then so this proof I gave you would then fail, right? You could bound it. So you could say, I'll truncate my interaction at some length scale, and I can run this argument for any length scale. I mean, that length scale could be 5 million, and the argument would then fail when I become sensitive to interactions that are more long range than that length scale. So that would be sort of exponential in the length scale at which I truncate. So if I had exponentially decaying interactions, then there would be a trade-off, right? At any given time, I would have a localized subspace, but the size of that localized subspace would go down as time increased, at least as far as the proof goes. But that's for these sort of strict proofs. Like what I'm going to talk about now is going to be robust even to some long-range tails to my interaction, exponential or even power law tails. So far I was talking about these exact eigenstates, but now within each symmetry block I have some exact eigenstates, but I also have some bigger symmetry subblocks. So now I can talk about the dynamics and the larger subblocks. And the dynamics in these larger subblocks, generically, it's thermal with respect to the subsector, by which I mean you don't have ergodicity in the whole symmetry sector, of course, but you do have ergodicity within that subblock. Not always. Sometimes you can get integrability within those subblocks, and then you break ergodicity even within the subblock. But that's somewhat special. It's not the generic case. The generic case is you get ergodicity within each subblock. And now you can meaningfully ask about the approach to thermal equilibrium and the dynamics if you pick an initial condition, which is in one of these big subblocks where you have some notion. It's a subblock with size that diverges in the thermodynamic limit, so you can meaningfully talk about equilibration, but now it's not equilibration to the full symmetry sector, it's equilibration to the particular subblock within the symmetry sector. Now, canonically, if you're looking at equilibration in systems with a conserved charge, the standard way to do it is, you use hydrodynamics, and the usual long-time behavior is diffusion. So what I've written down here is the diffusion equation for a conserved charge density rho. And if you solve the diffusion equation, you could even just do dimensional analysis. You conclude that there's a characteristic relationship between length scales and time scales, where length goes like square root of time. In the problem we're considering now, the approach to equilibrium is still going to be given by hydrodynamics, but it will not be diffusion. Instead, we'll find new universality classes for hydrodynamics. In fact, infinitely many new universality classes for hydrodynamics, all of which exhibit subdiffusion, meaning the approach to equilibrium is slower than the diffusion equation would predict. So how does that work? Well, remember the elementary mobile excitations are dipoles, and this straight away allows you to deduce that it can't be diffusion because the force on a dipole vanishes in uniform field. So if you apply uniform field, then you don't get any current. So the conductivity is 0. And if you're equilibrating, you can use an Einstein relation and say if the conductivity is 0, then the diffusion constant must be 0 also. So the approach to equilibrium better be slower than diffusion. What should it be? Well, now the mobile objects are dipoles, so the elementary sort of current should be some two-index object. You can think of it as flux of J-oriented dipoles in the I direction. And the generalized continuity equation should look something like this. So you could guess this, or you can derive it from Schwinger-Keldysh. And now what you need is you need to know what the dipole current looks like in terms of density gradients, and you can get that by standard thermodynamics, and you put it all together, and you conclude that the continuity equation involves the square of the Laplacian, or more generally, for the first n multiple limits conserved, you get a generalized diffusion equation which looks like this in the continuum. So here n is 0 is the ordinary case where you only conserve charge. Yeah, that's ordinary diffusion equation. N is 1 is charge and dipole, so now you get Laplacian squared. N is 2 is charge dipole quadrupole, Laplacian cubed, and so forth. Yeah? There's this infinite family of generalized diffusion equations characterized by how many multiple limits you're conserving. And you go and solve these, and you can even just do dimensional analysis, and you can satisfy yourself that there's this infinite family of subdiffusive universality classes where the length scale goes like time scale to 1 over 2 n plus 1. So if it was just charge, that's square root time, that's ordinary diffusion. If it's charge and dipole, it's t to the 1/4. If it's charge dipole quadrupole, it's t to the 1/6, and so forth. Again, this can be realized in our favorite example of cold atoms with a tilted potential. And in fact, it's already been observed at Wasim Bakr's group in Princeton, and it has this clean interpretation in terms of this fracton hydrodynamics. Again, no microscopic fractons in here. This is the hydrodynamics of a problem with some conservation laws that are motivated by the study of fractons. There's also other realizations which I'll skip in the interest of time. But I do want to mention sort of one more curious factor. So you take these hydrodynamic theories that we talked about, and it turns out that in addition to charge and dipole conservation, at least to the level of linear hydrodynamics, there's additional conservation laws. So you can define what we call harmonic function charges. So you take the charge density and you integrate it against f of r, where f of r is any harmonic function. Anything that solves Laplacian of f is 0. Yeah? And the charge that this defines is conserved at the level of linear hydrodynamics, both in infinite space and with appropriate charge and dipole conserving boundary conditions. Now you may think, hey, are we back to integrability and infinitely many conservation laws? Because after all, there's infinitely many harmonic functions. Well, not quite. These are not true conservation laws. Yeah? They're only there at the level of linear hydrodynamics. The moment you put in nonlinear corrections to hydrodynamics, the moment you put in lattice anisotropies, these are not conserved anymore. Yeah? So these conservation laws are fake. They're broken by lattice anisotropies. They're broken by nonlinear corrections to hydrodynamics. But what you can get is situations where the lattice anisotropies or the nonlinear corrections which break these conservation laws, where those are actually irrelevant thermodynamically. Yeah? So now the relaxation of these conserved charges actually relies on dangerously irrelevant corrections to hydrodynamics, and it can be even slower than the subdiffusion that the naive power counting from the Fracton hydrodynamics would predict. Yeah? So that's a sort of interesting curiosity that we discovered recently. Okay. I have 5 minutes left, yeah? Okay, so maybe I'll mostly skip this next section. Now, you could ask if there's any way to see this numerically. To see hydro numerically, you need very large system sizes. To do that, you need a new technique. We introduced a new technique. It's the technique of automaton Monte Carlo. What it relies on essentially is you have a special basis in which you can efficiently simulate things, because in that special basis, you don't generate entanglement. But for generic initial conditions, you have very complicated time evolution. So now you use Monte Carlo ideas. So you take a projection onto onto the special basis, time evolve that, take a projection onto another randomly chosen state in the special basis, time evolve that, and keep iterating and keep averaging what you get, and you just iterate until convergence, and this gives you a sort of computationally tractable and efficient way to simulate quantum dynamics with certain constraints for fairly large system sizes. And you can use it to verify the subdiffusive exponents, and we actually solved them in this way first numerically before we understood what was going on analytically. Okay, so to summarize the second part of my talk, when systems with these fracton type constraints thermalize, the approach to equilibrium is described by hydrodynamics, but it's not the diffusion equation. It's a generalized diffusion equation. And there's this infinite family of subdiffusive universality classes. We introduced a new numerical technique capable of exploring this, and the phenomenon has been observed in one experiment. So now to summarize my talk as a whole, non-equilibrium quantum many-body systems are terra incognita, and we want to find ways to evade equilibration. And the previously known ways to do this, like integrability and localization, rely on having infinitely many conservation laws. And we found a new way to do it with only finitely many conservation laws using physics inspired by fractrons. Fractons are a new kind of quantum state of matter, and their defining properties that the elementary excitations exhibit restricted mobility. And they've also provided us with this new frontier for quantum dynamics. The best known sort of exactly solvable lattice fracton models exhibit glassy relaxation, but they do equilibrate at finite time at any non-zero temperature. That's because the key fracton property really comes about from conservation laws on multiple limits of charge, and the standard fracton models have only Z2 type conservation laws. And the real payoff comes when we promote from Z2 to U1. So if you go to U1 conservation laws like U1 charge and dipole, then you get some very rich phenomenology. So you get robust and provable ergodicity breaking with a localized subspace that's exponentially large in system volume. This does not rely on disorder or on energy conservation, but it does rely on strict locality, as Steve discussed. Now if you start with an initial state that's in that localized subspace, then you have no charge dynamics whatsoever. But there's other subspaces where you do have charge dynamics, and some of those have size that diverges in the thermodynamic limit, and in there you have something that looks like thermalization and ergodicity, but now with respect to a subsector rather than the full symmetry sector. But the approach to equilibrium in those subsectors is subdiffusive, and this is completely robust to long-range interactions. You could add exponential tails, you could even add power law tails as long as the power was big enough. And you get subdiffusive approach to equilibrium. There's infinitely many subdiffusive aerodynamic universality classes. We've introduced new numerical tools to explore this, and the key phenomena have been experimentally observed by 3 different groups. And I think that is a good place to, maybe one more thing to say is, look, we continue to discover new surprises, like we just discovered these quasi-conservation laws, so I think there's still a lot to do here, and I think this is still a wide open frontier. And with that, let me thank various people. So a lot of people have been involved in this over the past few years. I think 4 deserve special mention. So this is Abhinav Prem, my first student, now postdoc at Princeton Center for Theoretical Science. This is Mike Petko, my first postdoc, now at the Department of Defense. This is Vedika Khemani, who you know. And this is my Boulder colleague, Andy Lucas, and also various other people that have been involved along the way. And with that, I will conclude.
There are questions from people. You can see whether there are questions from remote people.
Yeah, there isn't anything on Zoom yet.
So we have this one conservation law, or this we have 2, like the dipole and the charge conservation.
Yeah.
Is it reasonable to summarize this result as we can't have just these 2 conservation laws, we must have like some other large number of conservation laws which cause those sectors to split even more? Or is that like unreasonable to say?
Right. So the question is, could we interpret this as saying that having 2 conservation laws, charge and dipole, gives me many, many more conservation laws, which correspond to what subsector I'm in, right? So you're saying that, okay, within each symmetry sector, the problem further massively block diagonalizes into these many, many subsectors, and you would like to give each subsector its own quantum number. Okay, there's a couple of problems. The first, of course, is that these quantum numbers, these conservation laws are not there in the Hamiltonian object. I mean, they're not put in from the beginning, right? They emerge. But the other problem is if you look at the conserved quantities, they would be incredibly non-local. Yeah?
And that's
So,
for a fact. Like there's no
well,
construction that you can do with flow.
okay, I mean, at least I don't know, well, okay, let's back up. So it's always the case that if you go to the eigenstate basis, then the unitary matrix is diagonal, right? So I could always say, do I always have one conservation law per eigenstate? And what would that be? It would be the projector on the eigenstate. The projector on the eigenstate commutes with the Hamiltonian, so it's a conserved quantity. But it's totally non-local, so it's a crazy conservation law. Yeah. If I gave you a single eigenstate, like one of these localized eigenstates, what conservation law could you construct from it? And the only thing you could construct from it would be projector on that eigenstate. Which, yes, technically it's a conserved quantity, but it's totally non-local, so it's not what we usually mean by conserved quantity.
So
Yeah?
I guess what I'm thinking of is something along the lines of you have this smallest block
Yeah.
on a computational basis, which is local.
Yeah.
Perhaps from these projectors on each of the eigenstates of that block,
Yeah.
you can construct something that's like quasi-local.
Yeah, you can construct what looks like some integrals of motion, but now they depend on which state you're in. Yeah? And this again is very different from what we usually mean by integrals of motion, which is something that's true everywhere in Hilbert space. Steve.
So I'm having a hard time understanding how this is different from something that would be very mundane.
Mm-hmm.
So suppose I had something where that's a non-local multi-particle interaction. So if I have 100 particles that happen to be near each other, I give you some really big payment in energy. Okay, and then if I have but I have a Hamiltonian where only single particles can move at a time.
Okay.
Okay, so I take these little blobs of 100 particles, plop them down in places.
Okay.
And then there's no way I can move particles off mechanically because to take one off costs me a huge, immediately drop the energy, but I only gain the kinetic energy of one particle. I have to now steam off.
Right. So Steve, in this case, unless your blobs were infinite in size, you would just have a small matrix element, right? You would move one particle and then the next one and then the next one.
No, so I'm going to make a many-body interaction, not two-body interactions. I have an interaction that says, I give you a big energy if there are 100 particles touching each other, nothing if they're not.
But there will be some finite order in perturbation theory at which I can move the entire blob.
Yes, but it's going to be enormously slow.
Sure, but as a matter of principle, it will still be finite, right? So there will be some finite timescale beyond which this blob just moves. And beyond that,
probably set it up so it can't move. It would have to crash into something else.
So what this reminds me of is models of structural glass from, I guess, Maximov and Kagan and people like that, right? Yeah. Yes, so that's right. So that's localization in translation invariant settings. It's different in a couple of ways. So the first way in which it's different is that problem really relies on energy conservation. So if I had noisy, not energy conserving dynamics, there would be nothing like that. What I'm talking about here does not rely on energy conservation, right?
But it does rely on dipole.
It relies on dipole conservation, but not energy conservation. So it's
you certainly, I assume you can't have noise that violates dipole.
You can't have noise that violates dipole, but you can have noise which violates energy conservation. Then the other thing with those Maximov-Kagan type constructions is that, well, if you have periodic boundary conditions, of course, there's a uniform translation mode. Very slow, but it exists. But then there's all the bubble type obstructions, right? Where you say that, okay, you put down initial conditions. Generally, it's frozen. It looks almost like conventional localization, but there's rare regions where the local landscape is very uniform. Those can move around. Do they end up thermalizing the whole system? And now you're into the whole world of sort of rare region obstructions to localization, which the many-body localization community has spent most of the past decade arguing about, and At 0th order, there still isn't really consensus on what happens there, right? The nice thing about this problem is we don't have to have those arguments, right? I gave you this sort of pictorial proof, and that's it. This exponentially large localized subspace is there, proven QED, nothing to argue about. Yeah.
What about the ground state degeneracy?
Yeah, very good. So now what about ground state degeneracies? So for the discrete models like X cube and Haas code, yeah, well, if open boundary conditions, there's no ground state degeneracy. Yeah? Periodic boundary conditions, there's a lot of ground state degeneracy. So for the X cube model, the ground state degeneracy is exponential in linear system size. Yeah, so it's X of L degeneracy. For Haas code, it's exponential in linear system size, but it's also a very non-uniform function. So it depends on whether system size is a power of 2 or not. If you go to the U1 models, yeah, if you were actually in the sort of fractron type setting with gauge theories, then they're just gapless. So it doesn't make sense to talk about ground state degeneracy anymore. Yeah, so the ground state degeneracy is only there in the discrete models, but not U1.
Because of the photon?
Yeah, because of the photon.
Non-linearity is irrelevant at the subdivision.
Yes.
Is that true if you add those integration laws like energy?
If you add energy and momentum, then I do not know. But in this minimal sort of realization with where you just have charge and dipole and you don't demand energy and momentum, then non-linearities are just irrelevant at sort of tree level. But they could be dangerously irrelevant for these harmonic function charges.
Are there more questions? Okay, thanks.